we're going to do kind of circular acceleration of an object going around in a circle. So I'm not going to do this here, but we discussed in class the idea that if an object is going around in a circle, its speed may be constant, but the direction is changing, and the change in direction gives you a velocity. And actually, a kind of a cute way of seeing this is to remember that acceleration is v final minus v initial divided by t. And so that if I were just strictly going to take and subtract v final from v initial vectorially, I would have the following situation. So this is v final, and then v0 ends up looking like a vector. Now remember, it's minus, so I have to draw it in the kind of the opposite direction. So this is v final, this is minus v0, and you'll note that this gives me, this is v final minus v0, and sure enough it's pointed towards the center of the circle. So an object that is going around in a circle has a net acceleration into the center of the circle, and if there's where the acceleration, remember, is equal to the force divided by the mass, which therefore says there must be an inward directed force if an object is going around in a circle. So inward force required. Okay, so let's look at two relatively simple situations. Okay, first of all, we should define what circular acceleration gives us. It is, and we derived this in class, it's v0 over r, so therefore the inward directed force is mv squared over r, and we said that there's no such thing as centripetal force, but we have to go and get a force to do it. So it could be, for example, be tension, it could be friction, it could be a normal force, it could be gravity. For example, planets going around the sun are pulled into the center or caused to go in a circle because of the gravitational attraction between the planet and the sun. The other piece that is worth looking at is if I were to take a ball, and spin it around in a vertical circle, free body diagram here would have a downward tension and a downward mg, but at the bottom the mg would be again going down, but the tension would be going up. And in order if you were to look here, you can see at the top, you can write mv squared over r is equal to mg minus t, mg plus t, and therefore the tension is going to look like mv squared over r minus mg. And you can see that if I'm going too slow, that there's a minimum velocity, v minimum is going to equal the square root of rg, and you should confirm that. But at the bottom, the tension is always greater, right? There's always a positive tension, because if you again mv squared over r is equal to, in this case, tension is up, mg is down, and therefore the tension looks like mg plus mv squared over r. And even with a zero velocity, there's still going to be a tension. It's interesting if you look for just a second and think about this. What's going on at what I would call 9 o'clock. Well, there's an inward directed tension, and the mg force is straight down. So in this case, the tension is strictly equal to mv squared over r. And that mg force in some ways really doesn't contribute anything to the tension. Now in real life, if you want to keep it moving, things get a little bit more complicated. But for our purposes, at that point, if you were to look at strictly the tension force, it only depends upon the velocity. The only other piece that is worth remembering is that if an object is going around, I'm now going to have a car going around in a horizontal circle. The idea here is that the force of friction to make it go in a circle is inward directed. I have a normal force and I have an mg. And again, we're not going to cover this in the short term, but you'll remember that the force of friction is actually equal to mu times the normal force. Or in this case, for level surface, mu is equal to mg, so that you could write an expression which relates the minimum friction for a car to go around in a circle, mv squared over r is equal to mu mg, and therefore you end up with this kind of neat expression that says v squared is equal to mu g r.